Introduction. Geoengineering refers to the deliberate modification of Earth's natural systems in order to mitigate the impacts of climate change. As the world faces an escalating climate crisis, geoengineering has emerged as a controversial yet potentially pivotal field of study. The two main categories of geoengineering are carbon dioxide removal, CDR, and solar radiation management, SRM, each with distinct approaches and objectives. However, the science, ethics, and risks associated with geoengineering have sparked heated debates among scientists, policymakers, environmentalists, and ethicists. This essay explores the various geoengineering techniques, the controversies surrounding their use, and the potential future implications for humanity and the planet. Geoengineering techniques. 1. Carbon dioxide removal, CDR. CDR techniques are designed to remove carbon dioxide, CO2, from the atmosphere and store it in a stable form, either on land or in the ocean. These methods aim to reduce the concentration of CO2, one of the primary greenhouse gases responsible for global warming. The main CDR techniques include afforestation and reforestation. These methods involve planting trees or restoring forests to absorb CO2 from the atmosphere. Trees naturally sequester carbon through photosynthesis, and large-scale forest restoration could help offset some emissions. Bioenergy with carbon capture and storage, BECCS. BECCS involves growing biomass, such as crops, to absorb CO2, using it for energy production, and then capturing the resulting CO2 emissions and storing them underground. While BECCS holds promise as a CDR technique, concerns about land use, water resources, and the potential impacts on food production have raised red flags. Direct air capture, DAC. DAC involves using machines to capture CO2 directly from the air. The captured carbon is then either stored underground or used in other industrial processes. Although DAC is seen as a promising technology, it requires significant energy inputs and may not be scalable to the level needed to reverse the impacts of climate change. Ocean fertilization. This technique involves adding nutrients like iron to the ocean to stimulate phytoplankton growth, which would theoretically absorb more CO2. While ocean fertilization has received interest as a possible CDR approach, its effectiveness and the potential risks to marine ecosystems are still under investigation. 2. Solar radiation management, SRM. SRM techniques aim to reflect a portion of the sun's energy back into space to cool the Earth and counteract the warming effects of increased greenhouse gases. These techniques are not aimed at reducing CO2 levels, but instead seek to reduce the Earth's temperature through various methods. The most discussed SRM techniques include stratospheric aerosol injection, SAI. SAI involves injecting particles, such as sulfur dioxide, into the stratosphere to reflect sunlight. This technique mimics the cooling effects of large volcanic eruptions, which release sulfur particles into the atmosphere. While SAI could potentially lower global temperatures, it raises concerns about regional climate disruptions, ozone depletion, and unintended environmental consequences. Marine cloud brightening. This method aims to increase the reflectivity, albedo, of low-lying marine clouds by spraying seawater droplets into the atmosphere. By making clouds more reflective, this technique could theoretically reduce the amount of solar radiation reaching the Earth's surface. However, the effectiveness and feasibility of this method on a global scale remain uncertain. Space-based reflectors. A more futuristic SRM approach involves placing large mirrors or reflectors in space to reflect sunlight away from the Earth. While this concept is highly speculative and technically challenging, it represents a potential long-term solution for managing global temperatures. Controversies and concerns. Despite the potential benefits of geoengineering, its implementation raises a myriad of concerns. The following outlines some of the key controversies and risks associated with geoengineering. 1. Ethical and governance issues. One of the primary concerns about geoengineering is the question of governance and ethical considerations. Who has the authority to make decisions about the deployment of geoengineering technologies? Climate change is a global issue, And the effects of geoengineering interventions could transcend national borders, affecting ecosystems, weather patterns, and societies around the world. As a result, many argue that the global community must establish clear regulations and frameworks to govern geoengineering research and its potential deployment. There are also ethical concerns about the risks and unintended consequences of geoengineering. For example, if SRM techniques like stratospheric aerosol injection were used, it could potentially alter weather patterns and disrupt ecosystems in ways that are difficult to predict. The ethical dilemma is whether it is morally justifiable to manipulate the planet's climate system, even if the intent is to prevent the devastating effects of global warming. Additionally, geoengineering may disproportionately benefit wealthier nations that have the resources to implement such technologies, potentially exacerbating global inequalities. Developing countries, which are often the most vulnerable to climate change, may not have a say in decisions that impact their future climate and ecosystems. 2. Environmental risks and unintended consequences. One of the most significant concerns surrounding geoengineering is the potential for unintended environmental consequences. While the goal of geoengineering is to reduce the impacts of climate change, some techniques could inadvertently cause new problems. For example, stratospheric aerosol injection may cool the planet, but could also damage the ozone layer, which protects life on Earth from harmful ultraviolet radiation. Similarly, ocean fertilization could disrupt marine ecosystems, leading to harmful algal blooms, changes in biodiversity, and ocean acidification. The risks of geoengineering are not fully understood, and many of the potential consequences are difficult to model or predict. While some geoengineering methods like afforestation may seem relatively safe, others, such as SAI or large-scale BECCS, could have catastrophic side effects that may be hard to reverse. 3. Technological and financial feasibility. The technological feasibility of many geoengineering methods remains uncertain. For example, direct air capture requires massive amounts of energy to capture and store CO2 from the atmosphere. While there have been some advances in the technology, it is not clear whether it can be scaled up to the level necessary to make a significant impact on atmospheric CO2 levels. Additionally, the financial cost of large-scale geoengineering projects is enormous, and it is unclear who would bear the financial burden of these interventions. Moreover, there is the risk that reliance on geoengineering might reduce the urgency to reduce greenhouse gas emissions. Some critics argue that geoengineering could serve as a plan B that allows governments and industries to continue with business as usual while relying on technological fixes to address climate change. This could delay or undermine efforts to transition to cleaner, more sustainable energy systems and practices. 4. Moral hazard and dependence. Another criticism of geoengineering is the concept of moral hazard. If geoengineering techniques like solar radiation management were deployed, they could give the impression that climate change has been solved, even if the underlying cause, the accumulation of greenhouse gases, has not been addressed. This could reduce the pressure on governments and industries to take action on reducing emissions, further entrenching fossil fuel dependence, and delaying efforts to transition to a sustainable low-carbon economy. Moreover, there is the concern that once geoengineering techniques are deployed, they may become impossible to stop. For example, if stratospheric aerosol injection were initiated, stopping the process could result in rapid and catastrophic global warming, as the cooling effects would quickly dissipate. This creates a potential lock-in effect, where the world becomes dependent on geoengineering to maintain a stable climate, even though the long-term consequences remain uncertain. 5. Public perception and trust. Geoengineering technologies are often met with skepticism and fear from the public, primarily due to the perceived risks and uncertainties involved. A lack of transparency and oversight in geoengineering research can fuel concerns about the technology being deployed without adequate public consultation or regulatory frameworks. The playing God aspect of geoengineering, combined with the potential for unintended consequences, raises fears about humans tampering with complex natural systems. Public perception will play a significant role in determining whether geoengineering technologies can be deployed on a large scale. If geoengineering is seen as a silver bullet solution to climate change, it may undermine public support for more sustainable approaches like reducing emissions, transitioning to renewable energy, and changing consumption patterns. On the other hand, if geoengineering is approached with caution and careful governance, it could serve as a useful tool in addressing the climate crisis. Conclusion: geoengineering presents both a promising and perilous potential solution to the pressing issue of climate change. While technologies such as carbon dioxide removal and solar radiation management could theoretically help reduce global temperatures and mitigate some of the worst effects of climate change, they come with significant risks and uncertainties. The ethical, environmental, and social implications of geoengineering raise important questions about governance, justice, and the long-term consequences of tampering with Earth's natural systems. The controversy surrounding geoengineering is not just about the technologies themselves, but also about how society chooses to approach the climate crisis. Geoengineering should not be viewed as a substitute for reducing greenhouse gas emissions or transitioning to a sustainable, low-carbon economy. Instead, it should be seen as one of many tools in a broader portfolio of solutions, all of which must be pursued with caution, transparency, and global cooperation. Ultimately, the future of geoengineering will depend on how humanity balances the potential benefits with the risks and uncertainties, ensuring that any actions taken today do not compromise the well-being of future generations.